There's nothing to disclose. In clinical practice or research, full potential of MR angiography data is not used. To get accurate feature extraction, there are several steps to complete. The steps are to segment the data first, to get the global artery, then do the anatomical landmarking and labeling, and finally do the feature extraction. Even if we consider that we have the maximum accuracy at each of these steps, we will see that the final accuracy ends up being around 85%. In literature, it's quite evident that all the automated or semi-automated approaches suffer from insufficient and incomplete validation. In most of the studies, feature validation is not done, and for deep learning applications, the data requirements is clinically impractical. In this first example, this automated landmarking technique shows 88% accuracy, or even less in some complicated cases, even though around 50 subjects are being clinically required for training the UNet. And it lacks the feature validation part. In the second example, GNN-based deep learning result is shown, where the node identification accuracy and the edge accuracy is pretty great, but it needs 508 training subjects, which is impractical for clinical workflows. Also, it needs prior ICA information, which makes the method actually semi-automated. This brings us to the semi-automated approaches example. In this case, node and edge accuracy is 100% because a clinician will connect the dangling or disconnected arteries and landmark the connected points accurately. But this takes a long time, in average an hour and a half per subject. Most time goes in connecting the disconnected arteries properly. And in this approach, quantitative validation is only done for segmentation only, and artery features are qualitatively validated by manual tracing from a radiologist. So we are essentially solving the dangling and disconnected tracing problem because it increases the user interaction variability and the processing time and bias. And we want to establish a benchmarking framework that validates the features for the identification of efficiency and practicality of the automated and semi-automated methods that we have side by side. And also a synthetic data generation framework can actually give us a lot of data, and that can mitigate the data scarcity problem that we have for deep learning approaches for MR angiography. Now, to solve the disconnected and dangling vessel problem, we use this vessel fusing algorithm. The technique identifies hubs and junctions and iteratively represents them as subgraphs and results in an unique graph that has traces, nodes, and topological information. We call this vessel-fused network. So the vessel-fused network is actually generated at the artery graph generation stage. Before that, we have to segment out the artery and remove the extracranial arteries from there. And we use an unsupervised 2-class expectation maximization algorithm to do this. Then we do landmarking, and landmarking the graph is made very simple and intuitive in this toolbox. When the user completes and confirms the landmarking, the toolbox actually generates a dynamic table to account for missing arteries and in the complicated cases. Then finally, the following major arteries are reported and saved in an Excel sheet for each artery type. And this is how we simulate our data. We generate a 1D signal and map it to a 3D space and rasterize it. And basically, we do this for all the points that we have in the vessel-fused graph. This gives us the simulated data. We can map a plane and fit it to our arteries, and we can change the orientations of these arteries as well. So in this example, you were looking at two synthetic data that are generated by the same vessel-fused network, but different orientation of the arteries. So we have performed blind experiments for simulation and in vivo to compare our toolbox with iCafe. Significant percentage differences and correlation coefficients are reported for comparison. The segmented arteries we simulated and evaluated are highlighted here. Features used in the experiment was artery complexity, general morphological and topological features. Please note that the fractal dimensionality feature is unique to ArteryX. And high resolution and low resolution differences performance was shown for both methods. Ground truth feature comparison shows that our toolbox performs much better, having lower percentage differences compared with the iCafe. This is also reflected in the correlation of the features. A1 and A2 suggest that iCafe works best with high resolution data. In B1 and B2, we see the correlation with ground truth features, and ArteryX performs reliably than iCafe. In the group differences, we see the reflection of the simulation results. Distal sensitivity for some of the morphological and topological feature is quite apparent, which is not seen with iCafe. Correlating with age, we see some evidences that fractal dimension can be an interesting complexity feature for evaluating the arteries. Finally, we have included VR support for artery learning and labeling with our toolbox. So in summary, we have proposed a semi-automated feature extraction framework for the arteries, and the ArteryX framework has created a benchmark for artery toolbox comparison, and this will mitigate the training data requirements for deep learning applications in angiography. As we demonstrated that the features that we derive from our framework, it's more sensitive in a CSVD cohort, and also we showed that it's the same in simulation. I think this demonstrates a great potential for future clinical and population-based studies, since our approach takes minimal user intervention and the time in processing the intracranial arteries. This work was supported by NIH R3 grant. If you have any questions, please feel free to leave it online or offline. I'm happy to connect. And you can download the ArteryX toolbox in this QR code. Thank you.